the notes for lesson 9.1, polar coordinates. And our learning targets for this lesson are that you can graph polar coordinates, that you can graph simple polar equations, that you can find the distance between two polar coordinates. So we'll be looking at those learning targets real briefly in a second. But any ideas as to why we have polar coordinates at all and not just do everything in the XY plane? Because what?
Because someone was evil.
Someone was evil? No, no. Someone said that they just invented this math to torture you. No, not exactly. Why do we have math? Taxes, physics. What do we use it for?
Money.
Not just money. Measure stuff, calculate stuff. We use it to model real world stuff, right? And then try to understand it better and manipulate it if we can. So in the real world, is everything going to lay perfectly flat on a two-dimensional plane? Nope. So that's why in the last unit we looked at some 3D vectors. We looked at vectors in space, not just vectors in the coordinate plane. Also, there's this thing that for most of our history, geometry worked. Euclid's geometry worked. The line was a straight path that went on infinitely in both directions. And then later in our history, compared to the rest of our history, they learned something. Columbus helped them make sure it was true. But where Earth wasn't flat, it was actually more so spherical. So then, Euclid's geometry, by the way, those that go into, and some people theorize, but it wasn't the common belief, and they didn't have applied math for it or formulas or any of it. By the way, those of you who go on to higher levels of mathematics will not study Euclid's geometry so much because they'll expect that you've already mastered that. You'll actually study hyperbolic geometry, where a line isn't really a line, but more so a curve because it can be curved through space. Okay? And so you could have how many intersection points? Well, two. Two or one or none. So, but that's Euclid's geometry. You'll get into that somewhere else. Anyhow, if you looked at the Earth from above, would you see this big flat plane that we see with the XY coordinate plane? Of course not. So what are you going to see instead?
A circle.
Circle. And if you looked, you might see certain things falling on certain things. Somebody said longitude and latitude, well, not both of them, right? Here's another thing. The most common application of polar coordinates and how we've used them. There's other applications too, don't get me wrong, but the place that it's used most frequently, too bad Grace isn't here. She did one of her pieces on echolocation and sonar.
Oh, echolocation, that's in Finding Dory.
It is, but so anyhow, you're there, and you either listen for sounds or you can only listen out so far. So that's a certain radius, right? And so this spins around and around and picks up signals, either sonar or echolocation if you're actually sending a signal out, or just listening. And it gives you certain blips, and it tells you how far it is. Well, they use polar coordinates to do that. Thank you. Thank you. All right. So they use polar coordinates for that also. I'm flying a plane or steering a boat, and these two blips show up, and I want to know how far apart they are. I have to be able to calculate that. Okay? Now we have computers that we can program, and they do some of that, but before that, they had to do everything by hand. And sometimes they still do to verify stuff if their equipment's malfunctioning. So you need to know how to use polar coordinates, not just things in the coordinate plane. So we're looking at our first learning target, which is graphing polar coordinates. The polar coordinate system is made up of circles and radials, and each point in the polar coordinate system is r comma theta. So the first coordinate is how far away from the center, or what we call the pole. Pole is also known as the origin. How far away the radius will tell us, like which circle it is. Is it on a circle with radius 1 or a circle with radius 2? That's the distance it is from the center, or the pole. And then theta tells us, so r is the distance from the pole. And theta is how many degrees rotated from the polar axis. Or not necessarily degrees, but angle from the polar axis. Sometimes it's in radians. And so what we have is we have this circle here. We have the pole right in the center. And we have our polar axis. There's our polar axis. What would it be called if it was in the XY coordinate plane? It would sit right on top of what? The x-axis. So much like our unit circle, it's going to work somewhat like that too, in terms of rotating counterclockwise, like the unit circle. So it's going to match up nicely to our unit circle there. So we've got some point. This can be our little point. The distance from here to here is the radius of a circle that would be formed by that distance. And then the angle from the polar axis to there is our theta. Our polar axis is also called our initial ray. If we're thinking about vector paths, I could go straight this way, or I could turn and approach that point right there. In a polar coordinate, sometimes, and this is mind-blowing for some of you, because in geometry you're always told if it's a distance, the answer has to be positive, right? Because, hey, I did plus or minus the square root of 16 and I got 4. Well, then your radius is positive 4. Yeah, it is if you're talking about the length. The length is 4 units. But it is possible to have a negative radius. So if, of course, now it won't work. If r is negative, all that means is go to where it would be located if r were positive, and then go to the other side of the radial. So that means that that point lies on the opposite side of the terminal ray. For example, in the picture that we have, this is r right here. But if we had the opposite of r, I would actually look at this radial, this line, this diameter that goes through the center, and I'd first say, okay, I'm going to go to that point, but wait a minute, r is negative, so it can't be there. I'm going to go the other direction on this radial and put the radius here. That would be negative r. Theta would be the same. Let's say theta was 80 degrees. Well, I'd travel 80 degrees from the polar axis to here and say, oh, here's where it would be, but wait a second, it's negative. So I'm going to follow that diameter, that chord, to the other side. The same distance, but to the other side of it. It would actually, if I were looking at a positive radius, if I wanted to write this as a positive radius, I'd have to give it a different angle. Anybody know how many more degrees I'd have to add to theta to get it over here? 180. So we'll look at that in a little bit on how to, several ways that we can express polar coordinates and have the exact same point. For right now, just looking at graphing. Example 1 is graphing polar coordinates, which is our first learning target. For letter A, we're supposed to do it on 2, which is a radius of 2 and an angle of 45 degrees. Yes?
Can you scroll up?
Yep.
What did you say?
No, I didn't say anything about negative theta yet. We'll get there. All I said was it's possible for the radius to be negative. And so if it is, we just go to where the point would have been and go to the other side of our diameter. Same distance. So graph each point. We're going to go 45 degrees for this first one. We go 45 degrees from our polar axis, which there's our 45 degrees. And we go to the second ring out to represent 2 units away. Maybe it's miles or feet or whatever the units is. That's how far away we go. And that is point A. Point B is at negative 5 pi over 4. So you may need to pull out your unit circle. 5 pi over 4 is here. If I went backwards, it would be up. There, it would normally be at 3 pi over 4. For some of you, if you don't like negative angles, what could you do so that you can think of it between 0 and 2 pi? Add 2 pi to it. You're going to get 3 pi over 4 for this one. So I go out to the first circle and to 3 pi over 4 to plot point B. Did I mess up? Is that 2? No, it's right there. That first little dot, that was supposed to be a B. It's hard to see. I'll just do it in color so you don't get confused. The bigger dot was supposed to be a letter. It's hard, it's not writing very quickly. All right, so now we'll look at point C. I hope you can see it. We'll do that one in pink. We go to 100 degrees, which isn't on here, but we can put a line there just a little past 90. In fact, I'm going to make a full diagonal there going through the center and being at 100 degrees. So that's 100 degrees. That's what that line is supposed to represent since that's not on my unit circle. And I'm supposed to go to negative 1.5. So if I went from here to here, that's 100 degrees. And I'd go 1.5 would be right there, but I don't want it there, right? It's got to go where? 180 degrees further, or just, hey, it was here, sort of. Now I'm just going to come to the other side of the diagonal and go 1 point, or the diameter, go 1.5. There's point C. Point C is right here. It's on that same diameter, but it's instead of going up out to it, I go to the other side of the diameter, the other side of the pole. That's what makes it negative. Try this for letters D and E and F. Plot those points, see where you get them to land. We'll go over that in just a second. All right, so that's where your points should land for D, E, and F. Which one? For D. So negative 2 pi over 3 for D. Here's where 2 pi over 3 is, right? Negative 2 pi over 3, if you want, you're welcome to add 360 to it to see where it is on our unit circle. But I just went the other direction, that same amount. So here's the line for negative 2 pi over 3. But, so if it were 3, then it would be 1, 2, it would be here. But because it's negative 3, I have to go to the other side of my pole and move the point right there. That's where you go. Okay, that's all right. I did the same thing earlier, so I had them all over the place. So it might be helpful to have a unit circle or add 2 pi, and then it'll make more sense. Any other questions on how to find the points? You will, yes. Graph each point on the polar grid. Well, it's sort of the same thing, but it's actually getting at multiple ways of expressing the point. So I'd like you just to plot points H, K, and M for now. Try to plot those. Some of them have negative angles. You might want to add 360. Some of them have negative radii, or a negative radius. So there are your points for H, M, and K. Did anybody not get those? Yes?
Why is K in the first question?
So K is -2, -135. I don't like working with negative angles, particularly in degrees. So I did 135 plus 360 and found that that was actually an angle of 225. So it's -2, 225 degrees. So I went to 225 degrees, which is this radial right there. And I said, okay, 2 on that would be here, but it's a -2, so I have to take it to the other side of the pole and put it there. Now there's another way, if you really don't like working with R being negative, how far apart are they in terms of degrees? 180. So if I want to make that R positive, I could just do that 225 plus 180 to find it, okay? Or, yeah, I probably wouldn't subtract. Well, I could subtract 180 from it also. I could subtract 180 from it to get it in the unit circle. And then I'd see that it's on 45 degrees. So that might make it a little bit easier. Speaking of that, there's multiple ways to represent a point. Yes, Shelby?
So whenever the degree is negative, you just add 360 to it?
When the degree is negative, you can add 360. If you're really good, like some people, I'm going to clear the screen, hold on. Edit, clear, ink. Some people say, oh, -135. Here's where 135 is on my unit circle. That's right here. Well, instead of going this way, 135 degrees, I'll just go here. So if that makes sense to you and you can do that visually, then just do it that way. That's fine. But if you're like, I get kind of confused, particularly when it's in, I personally get confused when it's in radians. I tend to mess them up because my brain sees them in order this way. So then when you tell me negative, I have to like first figure out where it was this way and then do that. When it's in degrees, I normally can move it quickly in my head. So if you don't like working with the negative angles, just add 360 to get a coterminal. It'll be in the exact same location, but it'll be a positive angle. So multiple coordinates, there's a few ways to represent them. R comma theta, as we just saw, can be expressed in several different ways. It can have a negative radius with theta plus 180 or theta minus 180. We could also take any radius that we have, and theta could change, right? What could I do to get it in the exact same spot? Just keep adding what? 360. Adding or subtracting 360, which is the same as adding or subtracting 2 pi if it's in radians. So that would give me a coterminal angle, but it would be the exact same location. So yeah, you spun around the circle a couple times, but you still ended up at the same spot. When we are asked to find 4 different pairs of coordinates that name a point between -360 and +360, so between 2 pi and -2 pi, there's a process that we're going to follow to get those points. So I'm going to write that down over here, if it'll let me. Okay, it's not letting me do it, so I'll write it over here first. So the first point that we're going to find is, first off, what makes sense in the picture? Like, how many positive circle units is it out? Don't worry about having it as a negative radius. And exactly how far is it if you started at the polar axis? How many degrees within that one rotation? So getting your first point, the easiest point to obtain, the one that's the most logical to you. And then the second way to go would be to keep that radius, but this time you might subtract 2 pi units, or 360 if it's in degrees. And then the third way to write your point would be to express the radius as a negative value. But again, taking this original angle and you could subtract 180 or subtract pi units from it, and it would be, you know, they're 180 degrees or pi units away in terms of the angle when you have it negative versus positive. And then the fourth way that you could express that angle, so I guess I could have done this. You could have your opposite of your radius, theta plus pi. Honestly, 3 and 4 can be interchanged, because either way they're pi units away. If one has a positive radius and one has a negative. So this theta right here is coming from here. And the same thing here. It's the original theta that we had if we did our shortest angle measure from the polar axis to the point's location. So we're going to go through an example of this. Up here we have find 4 different pairs of order of coordinates that name point T. So it's still point T, still in the same place, just different ways of writing it. So we can see that this is 135 degrees for theta, and it's on the 1, 2, 3, 4th circle. So the most direct way to write the first point is going to be 4, 135 degrees. Now, after having my first point written down, I'm going to keep that positive radius of 4, but I'm going to do 135 minus 360. 135 minus 360 is negative 225 degrees. For my next trick, no, I'm just kidding. For the next point, I'm going to take the radius and change it. So now we're looking at, not here, but it would have been over here, but I'm going to reflect it back. But that's at, by the way, I could actually just look on the unit circle, 315. Hey, that's what I have. But the way to get it, if you didn't have your circle drawn, would be to take your original angle, the 135, and you could add 180 to it. I think I wrote subtract down here. Doesn't matter. 3 and 4 are interchangeable. One you're going to add, one you're going to subtract. And number 4, I have negative 4, and I'm going to do 135 minus 180. It'll give me a negative angle, but that's okay. And that's negative 45 degrees. So 4 different ways to represent the exact same point. 4 different ways it's going to be the exact same point when we graph it. Yes?
So like when the radius is negative and
Yes.
the angle is positive, that's when you like reflect it back.
Well, you're going to reflect it back anytime that radius is negative. So let's take a look at number 3. The reason this makes sense is if I go to 315 degrees, which is here, then I'd say 1, 2, 3, 4, oh, that's right here, except the radius is negative. So I have to go the same distance, which is 4 units, on the other side of the pole. It puts me right back here at point T. Does that make sense? And then this one the same way. Hey, you went negative 45 degrees, right to there at where same as 315, except it's negative, so I'd have to go the same distance, 4 units, but on the other side of the pole would put me right back there at point T. So all of these are point T, it's just different ways. If they only ask you to name it one way, this is the easiest, but you will at some point be asked to name it a few different ways. So try that for this problem where they've already given you the first way in radians instead of giving you a picture. They've given you the most direct path from the polar axis to pi over 6. And there's your point, 2 circles away from the polar axis. No, from the pole, sorry. Here's the pole. And that's 2 circles away. But you're going to find 3 other ways to express this using what we did on the front page. So by subtracting 360, by adding and subtracting 180 and making the radius negative. Except this time it won't be in degrees, you're going to do it in radians. the answers you should have gotten would be 2, negative 11 pi over 6. Still within the unit circle at 2, negative 11 pi over 6, or within negative 2 pi. Negative 2, 7 pi over 6, and negative 2, negative 5 pi over 6. Any questions on how to get those? So to get this one, I just took theta and subtracted 2 pi, which 2 pi, so it's pi over 6 minus 12 pi over 6. Led to this one. This one I changed the radius, so I just had to take pi over 6 and add pi units, which was 6 pi over 6, so that's where you got the 7 pi over 6. Then on the other one I had to subtract it, which gave me negative 5 pi over 6. All right. Graphing, before we get to graphing equations, when I say simple equations, it's basically equivalent of doing this in the x, y axis. Here's x, here's y. Everybody should be able to graph. X equals negative 3, or even the equation, y equals 2. Which one of these is horizontal? Y equals 2. So there's my y equals 2. And my x equals negative 3 is back here. Horizontal and vertical lines. Well, it's not necessarily going to be horizontal and vertical lines in a polar coordinate system. But the same idea remains. I don't have any interaction or any function relating the x coordinates and the y coordinates per se. There is, but it's more hidden. It's a little simplistic. So we're going to look at that with these. For the first one, we have a radius of 2 for letter A, and for letter B, we have a theta of pi over 6. Which one of these do you think is going to give us a line? If you think it's A, you can clap twice. If you think it's B, stomp your feet once. Which one's going to give us a line? R equals 2, or theta equals pi over 6. So you're going to clap twice if you think it's going to be A. Stomp once if you think it's going to be pi over 6. Which one's going to give us a line? A or B? A or B? So some of you are voting B. I didn't hear. Other people are like, I have no idea. Some people didn't clap. Let me ask this a different way. Which one do you think is going to give us a circle? A or B? Hey, Sean. I think it's A. A? Radius of 2 is going to give us a circle. Okay? From the pole, every point out on it has a radius of 2. So that's our circle. Just like, by the way, this is how we're going to eventually go back and forth between polar coordinates and points in the xy plane. You guys know how to write an equation of a circle. When the center is at the origin in the xy plane, what's the center? The point for the center is 0, 0. And so in the xy plane, we have x squared plus y squared equals r squared. So this equation would actually be equals 4 in the xy plane. And it would look just like this if this were our x-axis and our y-axis. I'm getting ahead of myself, though, because that's not in today's lesson. So don't panic if you're like, what? Where'd that come from? All right, so, but here it's just as simple as saying the radius is 2. You've got a circle. When they say theta equals pi over 6, I'm going to go to pi over 6, which is right here. And I'm just going to do every point on that line, because they didn't tell me what the radius is. The radius, this means for all values for the radius can be anything from negative infinity to positive infinity. So this is a line extending infinitely this way. Here, theta can be anything from negative infinity to positive infinity in terms of degrees or radians. So that's why it's just every single point on this thing. Any point that you could fit in between or keep rotating around it still gives you the same circle. Try that for letters C and D. All right, so we have this circle for letter C, and for letter D, we have this line extending to infinity and beyond. Polar distance. The formula is going to look really familiar, so I don't want to give it to you yet. Unlike the xy coordinate plane, I can't just subtract x coordinates to get the horizontal distance and y coordinates to get the height. Instead, I want you to think about each one. You don't need to write any of this down yet. Instead, what I have is this. Whoa. I have a point here whose r sub 2 units away from the pole. I don't know what that, I do know that length. I don't know what it is for this because right now it's just a variable. But I know what the radius is for that point, what the distance from 0 to P is. I would also know, if I know where this point is, its coordinates, what the distance from O to P sub 1 is. So that would be R sub 1. So those are numbers. I actually know them. I would also know, and I think I want to exit full screen to be able to do this. I would also know this theta, the distance from here to here. That would be theta 1. Don't write any of this down yet. And wait, I don't want that. So I've got theta 1. And then I'd have this theta from here to here. So how would I find the angle right here, that angle, if I know those two angles? So basically I have this. I have this, which is theta 1, theta sub 1. And I have this, which is theta sub 2. How do I find this angle right here? Subtract the two angles, right? And then I've got that angle. So this angle, I'm just going to call it theta star, equals theta sub 1 minus theta sub 2. Well, let me erase that picture real quick and get rid of some of this mess up here. So I still have this distance right here and this distance right here. And now I actually have this angle right here. And what I'm trying to find is the distance from here to here. Does anybody know what we're really using to solve this problem?
No.
Can't use that unless it's what type of triangle?
Right.
I need a right triangle used Pythagorean's theorem. Let me draw it a little bit bigger for you and outside of the coordinate plane, and then just remember R1, oh, this is R2 actually. R2 and R1 and theta are actually numbers that I actually have the numbers for. And I'm trying to find this sucker, I'm calling it X. It's the distance between the two of them.
Inverse.
Can't use the distance from this on the XY coordinate plane. What shape do I have? Triangle. But it's a non-right triangle, or it could be a non-right triangle. So if it's not a right triangle, how do I solve a triangle when it looks like this? Side angle side is the setup, so it's what law? Law of cosines, right? X squared equals r sub 1 squared plus r sub 2 squared minus the product of r sub 1. Oh, I forgot to put a 2 in front. 2 times r sub 1 times r sub 2 times the cosine of theta, which we found by doing subtracting the two thetas. Well, that's exactly where our formula is coming from. They want the actual distance, not its squared. So this thing right here is going to be our formula that we're going to put right up here. The distance between 2 points in the polar coordinate plane, when the first point is r sub 1 comma theta sub 1, and point 2, p sub 2, is r sub 2 theta sub 2, you can calculate the distance between those 2 points by doing the square root of r sub 1 squared plus r sub 2 squared minus 2 by r sub 1 by r sub 2 by cosine of the angle that's formed when you do theta 2 minus theta 1 or theta 1 minus theta 2. It honestly won't matter. I'm just rid of that. One of them could be negative. It'll still work out. It's okay. So here's our polar distance formula. And yes, it should look familiar because it's all it is. Oops, I need to carry that around. Is a law of cosines with those values. So if you got stuck and you recognize that it was this triangle, you can do it. Hopefully. You've done law of cosines quite a bit. So here's an application problem. Gee, one of those most frequently used arenas, naval radar or airline radar. Tracking 2 aircraft carriers. The coordinates of the 2 carriers are 8, 150 degrees and 365 degrees. And where R is measured in miles. So it's 8 miles away at 150 degrees to the polar axis and 3 miles away at 65 degrees to the polar axis. So here's our polar axis. Here's our 1.365 is roughly over here. Roughly there at 365. And then the 150 is right there. I was right. Oh, wait, I can't do that because I'd have to make how many more rings? I need to make more rings, so I'm going to have to scale it to make it fit. Forgot about that, sorry. So this is 2, 4, 6, 8. Who do we appreciate? Hey, you got it right. I'm just kidding. Anyhow, so here's 3, 65 degrees roughly. Had to change it. And then 8, 150. 150 is over here, so there's 2, 4, 6, 8 would go here. So the 2 red points, I know there's 3. 2 red points are where I've seen them on the radar. I want to know how far apart they are from each other. Hey, no, it's black. So I'm just going to use the distance formula for polar coordinates. Here's a sketch of the graph. Find the distance between those 2. See if you can do that. Square root of 8 squared plus 3 squared minus 2 by 8 by 3 by cosine of 150 minus 65. Did you get roughly 8.3 miles? Then you got it right. Does it matter whether I did 150 minus 65 or 65 minus 150?
No.
Nope. Let's take a look if we get the same answer or not. Why isn't this working? There we go. 65 minus 150.
Okay.
Same answer. Yay. All right, there you go. Let me hit stop and get you the assignment.